We've seen how to estimate the beta parameters in the simple linear regression model, but there is one more parameter in that model that needs to be estimated. That parameter is the variance of the error terms, and deriving that estimator is what we're going to do in this lecture video. So here's an outline of what we'll be looking at in this lecture. First, we'll quantify what we mean by the total variability in the response variable. Once we've done that, we'll partition that total variability. And in conjunction with that, we'll do a few more things. First, we'll partition the total degrees of freedom that are available to us. We'll also quantify the proportion of variability in the response that is accounted for by the fitted model. We'll then provide the expected values of the sums of squares that comprise that partitioning of the total variability. We'll then define mean squares from those sums of squares and find their expected values. And then finally, once we've done that, we'll be able to obtain an unbiased estimator of the variance of the model error terms. So let's first look at partitioning the total variability of the response. So recall from a previous lecture that we defined notation S sub yy to represent the corrected sum of squares of the response variable y. So S sub yy, the corrected sum of squares of the response variable, is the sum of the squares of the differences between the observed values of the responses, y sub I, minus the mean of those responses. This is a measure of the total variability in the response variable. Now this quantity is also denoted by TSS, an abbreviation for the total sum of squares, and we're going to use this notation in the present context. The next slide shows a representation of this in the context of a scatter plot. So here's a quick graphic that I created on my iPad. And so we see here a scatter plot of data points, which are represented by blue. The arithmetic mean of those of the y values of those data points is located at the point on the vertical axis, denoted by y bar. And then the blue line corresponds to the least squares line for that data. Now notice that I have drawn dotted vertical lines from each of the observed data points to the horizontal line corresponding to y bar. And the sum of the squares of those differences is the total sum of squares, TSS, for this data set. Now the total variability in the response, TSS, can be partitioned in the following way. So TSS, which is the sum I going from 1 to n of the square of the differences y sub I minus y bar, can be partitioned by subtracting and adding y hat sub I within the parentheses. And so when I do that, I'm just adding 0 to that quantity, so I haven't changed it, but I'm just representing it a little differently. And then when I expand that binomial, it becomes this sum of 3 terms. The first term, the sum I going from 1 to n, of the sum of the square differences between the observed value of y and the predicted value of y. The second term is the sum I going from 1 to n of the square of the differences between each predicted value, y sub I hat, and the average of the observed values of the y's. And the third term is 2 times the sum I going from 1 to n of the products y sub I minus y hat sub I, so the difference between the observed value of y and the predicted value of y, times the quantity, times the difference, the predicted value of y minus the mean of the observed y values. Now it can be shown that the cross product sum is equal to 0. So the sum I going from 1 to n of the product of y sub I minus y sub I hat times y sub I hat minus y bar, the sum of those cross products is equal to 0. Now, what does this result look like in the context of the scatter plot? So to the previous scatter plot, I've added a few features. The first is corresponding to each of the observed data points, I've indicated the predicted data point on the least squares line. And I've indicated those predicted points in black. In addition, I have now two sets of differences, denoted A and B. The differences denoted by A correspond to the differences between the observed value of y and the predicted value of y. And the differences indicated by B denote the differences between the predicted value of y, the point on the line, and the value of y bar, which is the mean of the observed values of y. Now, the sum of the cross product terms is equal to the sum of the products of the A's and the B's. So A1 times B1 plus A2 times B2 plus A3 times B3 plus A4 times B4. Now notice, and we have to be careful that we take the differences in the correct way, but notice that the first term, A1 times B1, is negative because A1 is positive and B1 is negative. On the other hand, A2 times B2 is positive because both A2 and B2 are negative. The term A3 times B3 is positive because both of those values are positive. And finally, A4 times B4 is negative because A4 is negative and B4 is positive. So two of the terms are negative, two are positive, and so it's at least conceivable that they add to zero, but it turns out that they actually do, the sum actually adds to zero. Now, it may not be obvious from this graph that the sum of the cross products is equal to zero, but it can be shown algebraically that that is the case. But I wanted to show you this graph because this is, at least graphically, what it is telling us. Now, this result, that the sum of the cross products is equal to zero, implies that the paired values, y sub I minus y hat sub I, and y hat sub I minus y bar, that those values are orthogonal. Now, since the sum of the cross product terms is zero, it follows that the total sum of squares, TSS, can be partitioned into two components. So TSS is equal to the sum, I going from 1 to n, of the square of the differences between the observed values of y, y sub I, and the predicted values of y, y hat sub I, plus the sum of the squared values of the differences between the predicted value of y, y hat sub I, and the mean of the observed values of y, y bar. Now we call these two sums of squares SSE and SSR. Now the component SSR, which is an abbreviation for the sum of squares for the regression, is the sum of the squares of the differences between the predicted values, y hat sub I, and the overall mean of the response, y bar, and it is a measure of the variability in the response that is accounted for by the fitted model. The next slide shows this in the context of our scatter plot. Now in this graphic, I've left out the observed values because all we need are the predicted values and the overall mean of the observed values of the response. And so the sum of squares for the regression is equal to the sum of the squared differences between the predicted values and y bar. And so you can see here that I've got the differences between each predicted value and y bar indicated in the vertical blue line. And then when we square those differences and add those up, we get SSR. The component SSE, which is the sum of squared errors, is the sum of the squares of the differences between the observed values and the predicted values of the response. This is a measure of the variability in the response that is not accounted for by the fitted model. Now recall that the least squares estimators were chosen to minimize this value. The next slide shows this in the context of the scatter plot. And so in this scatter plot, I have my observed data again, and I have my least squares line with the predicted values for each of the x values indicated on that least squares line in black. And the SSE is the sum of the squared distances or differences between each of the observed values, the blue points, and the black points on the line. Okay, next we're going to, in conjunction with this partitioning, we're going to partition the total degrees of freedom that we have available to us. So let's first talk about the total number of degrees of freedom that we have available. So let's think of the n responses, y1, y2, and so forth up to y sub n, as comprising a single point, which I'll denote by bold y, in n-dimensional Euclidean space. Now, the fact that the mean of the y values is a linear combination of the y values, this induces a single linear constraint among the n values, y1 through yn. This relationship, represented by this equation, which is also a constraint, implies that the point bold y is not able to freely move throughout all n dimensions. In fact, it can only move freely throughout n-1 dimensions, because given the values of any of n-1 of the responses, the value of the remaining response cannot take on any value, but rather must satisfy the equation shown above. Because of this, associated with the total sum of squares, TSS, we say that there are n-1 degrees of freedom. Corresponding to the partitioning of the total sum of squares into the two components, SSR plus SSE, there is a partitioning of the n-1 degrees of freedom associated with TSS, so that the number of degrees of freedom associated with TSS is equal to the degrees of freedom associated with SSR plus the degrees of freedom associated with SSE. The following slide shows the partitioning of the total degrees of freedom corresponding to this partitioning of TSS. And so here I have a partial ANOVA table. You can see here that we have the first three columns of an ANOVA table, the first column being the source of variation, the second column containing the sums of squares, and then the third column containing the degrees of freedom associated with each source of variation. And so at the bottom we have the total variation in the response, that the corresponding sum of squares is TSS, and the degrees of freedom associated with TSS is n-1, as we've seen. In the first row we have, as a source of variation, the regression model itself. The sum of squares corresponding to that source of variation is SSR, the sum of squares for the regression, and associated with that sum of squares there is 1 degree of freedom. In the second row, we have as a source of variation the error. The corresponding sum of squares is SSE, and the degrees of freedom associated with SSE is then necessarily n-2. And this is necessary because the degrees of freedom associated with the regression and the degrees of freedom associated with the error term must total the total degrees of freedom to us, which is n-1. Now, while we're at it, let's take a look at how to quantify the proportion of variability in the response that is accounted for by the fitted model. Dividing both sides of the partition by TSS gives the equivalent equation, 1 equal to SSR over TSS plus SSE over TSS. The ratio SSR over TSS is the proportion of the total variability in the response variable that is accounted for by the fitted model. Now, this quantity is called the coefficient of determination and is denoted by r squared, so that 1 equal to r squared plus SSE over TSS. Note that r squared will always be between 0 and 1, with values closer to 1 indicating better fit to the existing data, while values closer to 0 indicating worse fit. The ratio SSE over TSS is the proportion of the total variability in the response that is not accounted for by the fitted model. All right, next what we're going to do is find the expected values of the sums of squares comprising this partitioning. So by the linearity of the expectation operator, the expected value of TSS, which by substitution would be the expected value of SSR plus SSE, is equal to the expected value of SSR plus the expected value of SSE. It can be shown that the expected value of the total sum of squares is equal to beta 1 squared times the corrected sum of squares of the x's, s sub xx, plus n minus 1 times sigma squared. In addition, it can be shown that the expected value of SSR, the sum of squares for the regression, is equal to sigma squared plus beta 1 squared times s sub xx. Solving this equation for the expected value of SSE gives the expected value of SSE equal to the expected value of TSS minus the expected value of SSR, and that turns out to be n minus 2 times sigma squared. So to summarize, the total sum of squares can be partitioned into two components, the SSR and SSE. By the linearity of the expectation operator, the expected value of the total sum of squares is equal to the expected value of SSR plus the expected value of SSE. And the expected values of these components are as follows. The expected value of TSS is equal to beta 1 squared times s sub xx plus n minus 1 times sigma squared. The expected value of SSR is equal to sigma squared plus beta 1 squared times s sub xx. And finally, the expected value of SSE is equal to n minus 2 times sigma squared. Okay, now that we have the sums of squares, we're going to define mean squares in terms of those sums of squares, and we're going to find their expected values. So first, let's define the quantity MSE, which is equal to SSE divided by n minus 2. Note that I'm dividing SSE by its degrees of freedom. By the linearity property of the expectation operator, then, the expected value of MSE is equal to sigma squared. This quantity is called the mean squared error. Note that because its expected value is sigma squared, the MSE is an unbiased estimator of sigma squared, the variance of the model error terms. We'll denote this estimator of sigma squared using hat notation in the usual way by sigma hat squared equal to MSE. Next, define the quantity MSR to be SSR over 1. And notice here that we're dividing SSR by its degree of freedom as well. By the linearity property of the expectation operator, then, the expected value of MSR is equal to sigma squared plus beta 1 squared times s sub xx. Now this quantity is called the mean square for the regression, and the MSE is an unbiased estimator of the quantity sigma squared plus beta 1 squared times s sub xx. So here's a summary of what we've done. We partitioned the total variability in the response variable, and then we use this partitioning to define a measure called the coefficient of determination, which is denoted by r squared. This gives us the proportion of the variability in the response variable that is accounted for by the fitted model, and it's a measure of the quality of fit of the fitted model to the existing data. We then presented the expected values of the sums of squares. We also partitioned the total degrees of freedom. We then defined the mean squares as the sum of the squares divided by their corresponding degrees of freedom, and we found their expected values. And once we had done that, we were able to come up with an unbiased estimator of the variance of the model error term. So that's all I wanted to show you in this lecture video. I'll see you in the next lecture video.